Example 4, agricultural suitability for durian fruit in the tropical Philippines. Before undertaking any analyses with multiple raster layers, or even multiple vector layers, you need to ensure that you have all of your layers in the same coordinate system or map projection. And that's done using the project tool in the geoprocessing pane, data management, projections and transformations project. So that tool we'll be using today to change coordinate systems for some of our layers so that they all have the same coordinate system prior to any analysis. Moreover, all layers should be resampled to the same resolution in the same coordinate system. So any overlay analysis is only going to be as accurate as the least accurate layer. And in the Durian example, we have elevation. Elevation is an approximately 90 by 90 meter cell size. It's what's called a 3 arcsecond data set. And the cell size that we are going to be analyzing things at is 1,000 meters by 1,000 meters, because those are the least accurate layers that we have in our analysis. So when we talk about, for example, resampling here, we're using it as a general concept of changing cell size and resampling the original cells to match up or transform into a new cell size. So in this context here, when I talk about resampling, I'm not meaning the resample tool necessarily, but the concept of resampling. And we have to control that to make sure that we resample things appropriately. Because remember, ArcGIS will allow you to use multiple layers together in the same analysis that aren't even of the same type or the same coordinate system. So you can mix raster and vector, and they can be in different coordinate systems. But what happens is ArcGIS makes assumptions. Let's say you have a vector layer, that it will transform it into a raster layer at a cell size using a combination of resampling, using nearest neighbor as the default only. That's the default way it does it in the background. So you never see that happen. So it actually creates a raster layer that you never see, and then transforms it into the coordinate system of your current raster layer using nearest neighbor resampling, and then does the analysis with those two things, and then outputs a result. And you never see that intermediate stuff happening, so you have no control over it. And often it's inappropriate. We know, for example, that nearest neighbor is appropriate for categorical data, but even better is majority. And nearest neighbor is also appropriate for numeric data, but it's not the best idea to use. We want to use something like bilinear interpolation, which is something that follows the assumption that continuous data is in fact continuously divisible across space. So we must control these things prior to analysis. That means a very large data step in the real world. And this is an example that is a little bit more like the real world in that it has multiple things that have to be done to the data beforehand. So the Philippine government wants to find new areas to grow durian fruit for domestic needs and export growth. Why? Because durian is the king of fruits, it's highly sought after, and it's very profitable. Now, durians, though, are extremely sensitive. They've evolved in a pure tropical climate. They can't even survive at temperatures less than 7 degrees Celsius. So if a temperature reaches 7 degrees Celsius, it might as well have reached minus 20. It's the same to the tree will die. So it's best to plant trees for large cropping of durian in areas where the coldest month never gets lower than 12 degrees Celsius. So that's just to ensure that you don't have some sort of thing happening whereby the Durians will end up dying because of some weird cold snap or something. And islands like the Philippines are slightly less prone to having cold snaps within the tropics because they're surrounded by ocean, which really mediates the temperatures. It doesn't let large continental air masses necessarily cause freezing temperatures. Now, there have been freezing temperatures in the tropics at sea level. Hong Kong, it's not unusual for Hong Kong, for example, to have 0 degrees Celsius days in the winter. It's not unusual for parts of India, continental India in particular, to have 0 degrees Celsius or even lower in the winter, like around Bhopal, India and stuff like that. But on islands, you're a bit safer. So 12 degrees Celsius for the coldest month should be fairly safe from any aberrant cold snaps. Durians also need a lot of water. So they need between 1.6 to 4 meters of water rainfall per year because this is a rainforest tree. So we need to know where we have that much rainfall each year. So we need temperature, we need precip, called precipitation for rainfall, and then soil types. Well, durians can grow on a range of soil types for optimal growth and health. They like a loamy, well-draining soil. So lots of rainfall, but they don't like standing water, for example. They can't grow in areas that are constantly moist in the soil because they'll suffer root rot. So they do prefer a well-drained soil that is on land between 1 and 5 degrees. Anything greater than 5, you get too much drainage, even when you have large precipitation. Anything less than 1 is too flat for an area of the amount of precipitation that it required for the tree, so it would end up having root rot. So we need these two things. We need soil, and of course, we're talking about here slope. So we need slope, which comes from a DEM. So there's a bunch of layers that we require: temperature, precipitation, soil, and an elevation model to get slope. So it's a fairly large data step here. And of course, in the real world, you'd have to source this data. I've already done that for you for this example. So I've given you all the data we need. 4 layers are required, and we have names for each layer. We have soils, total rainfall, coldest, that's a minimum temperature of the coldest month, and elevation. And we'll see these when we do the example in ArcGIS Pro. So we make a little table like this just to see what we're working with. So we list our layers and then the spatial references for each layer. The first 3 are in the same spatial reference or coordinate system. The last one is not. So most of them are in WGS 84, World Geodetic System 84, UTM 51 North. Elevation, however, is in WGS 84, longitude latitude. So if it just says WGS 84, we know that's longitude latitude. There's nothing else after the WGS 84 to say, well, these WGS 84 coordinates were projected into this system, such as the 3 examples above, where we know WGS 84 is the longitude latitude system that was projected. Its datum, its ellipsoid, was projected into UTM 51 North. So it would make most sense to transform everything here, in this case, to transform elevation, I should say, into the UTM 51 North system for 2 reasons. One, it makes sense because of the amount of work that's involved. Why would we want to transform all 3 into the WGS 84 system? Secondly, the WGS 84 system is not really appropriate for analyses that require computations of distance like slope does. Because from the south to the north of the country, the width of a cell will be larger to smaller as we go north in the Philippines. And so slope calculations will be biased by that. So we really want to analyze our rasters whenever possible in a projected coordinate system, where 1 meter of x is equal to 1 meter of y, no matter where we are within our study region. So we know we have to do one conversion here to that coordinate system using the project tool in data management. Then we look at the format of each one. Soils is vector. The rest are all raster. So that means there's also going to be an encoding having to be done here. So a raster encoding where we encode the soils information from vector to raster. And then finally we look at the resolutions. Well, the vector layer, we have no cell-based resolution because we don't have one. It's a vector layer. We could have a base scale that it was created at, but we don't know. But we'll assume that it's something smaller than 1 to 1 million in scale. So the vector layer has no cell size right now. The middle two have a 1,000 meter cell size, and the smallest one has something in decimal degrees. So 0.00083 decimal degrees is equivalent to 3 arc seconds. So 3 seconds of arc being 1 degree. And so it's quite small. In the real world, that is equivalent to approximately 90 meters by 90 meters per cell at the equator. And the southern Philippines is very close, near the equator, right? But as you go north, you get further from the equator. And so that's no longer 90 by 90. It would be 90 in height at the equator. As we go north of the equator, it could end up being 90 in height, but as little as 80 in width. So it's approximately 90 by 90, which is the best approximation we can get because it's variable from north to south, even though it's a constant 3 arc second cell. Now, what we also notice then is that our coarsest layers are these two in the middle, rainfall and temperature of the coldest month. So we'll have to transform or undertake a resampling type process to bring the elevation to 1,000 meters. And there, you'll see the proper way of doing that, to scale up elevation. And soils. Once we encode it to raster, we could encode it to 1,000 meters, for example. So we have to, our target cell size will be 1,000 meters. So in terms of the things that have to be changed, we have these two layers, soils and elevation. So the soils is vector, and elevation is raster in the wrong coordinate system and wrong cell size. Soils is vector, has no cell size, it's in the right coordinate system. So the data step here is very large before we can actually build a model to find out where within the Philippines it would be suitable to grow durian under the conditions that we have previously mentioned. So as usual, environments are set, application level environments, and we will use the total rainfall layer. So that is one of the layers that is already in a raster with a cell size of 1,000 meters as the control layer for all the critical environmental settings. The output coordinate system, the cell size, the extent, the snap raster, and the mask. And you could do the same thing in Python. So if you're doing Python, again, for the first session of the day, you want to make sure you set your Python data. So if you've already done already set your application level settings, the global environment settings, you can skip this step here in the Python window. Just skip that part. Since once we do ArcPy reset environments, it'll automatically into the Python window accept the global environment settings as the ones that will be used. So our least accurate layers are total rainfall and temp coldest. The two rasters are both in a Cartesian coordinate system, WGS 84, UTM 51 north. The Cartesian part is the UTM 51 north. but those were all coordinates are coming from an ellipsoid called the WGS84 ellipsoid. The soils layer is in the same coordinate system as the other two that we just said here, but it's a vector layer. So it'll have to be encoded to raster, and we can encode it and resample it at the same time to a 1,000 meter. Elevation is a raster in a geographic coordinate system that has 3 arcseconds. It has to be both projected while maintaining that cell size of approximately 90 by 90 meters, and then upsampled or upscaled to 1,000 meters. That upscaling process will utilize block statistics. Excuse me. Now, we have these two layers, which both have the same coordinate system and the same 1,000 meters cell sizes, so 1 kilometer cell sizes. So the total rainfall and temp coldest both have a 1,000 meter by 1,000 meter cell size, or 1 square kilometer cell. That does not mean in any way that they automatically match up, even though they're both for the Philippines. So it doesn't mean that the cells in total rainfall and the cells in temp coldest coincide exactly when they're overlaid in GIS. That must be checked. So just because you have two layers that are raster for the same area and they both have the same coordinate system and cell size, you can't assume that they have perfectly snapped coincident cells. So there's a number of ways you can check. You could bring them both into ArcGIS Pro, zoom in on the cells, zoom in on a cell or where you can see the cells individually, turn the top one off to see the bottom one, see if the cells are in exactly the same place. Or you can use this little equation here, which just subtracts the X-max values and modulus divides by 1,000, the cell size. And if there's no remainder for this statement, so if it prints out 0, then we know that they're aligned, both rasters are aligned in the X-max system, so at the maximum X values. So they're aligned bottom and top, or bottom, I should say in this case top. No, sorry, not bottom or top. This is going to be right. So they're going to be aligned to the right. And then you change X here and X here to Y. And if it's 0, you know they're aligned at the top as well. So you know then at that point that if both those things come out as 0, that you have aligned layers. So 2 ways again to check that. One is zooming in and looking at the cells in both of them. The other is just doing a more exact one here, which is to check if they actually have the same min and max coordinate values for the rasters. Either way is fine, although this is more exact. And I'll tell you right now, they both have the same, they do align, so it's fine in this case. So looking at again, this is the data step here. We have to take soils, remember it's in vector, and make it into a 1,000 meter by 1,000 meter raster that matches up with our total rainfall. So in this case, we can use the polygon to raster tool, and we'll use the maximum area. So the maximum area or maximum combined area to determine which soils or how soils will be aggregated to 1,000 by 1,000 meters to the 1 square kilometer cell size. So that's done. We can put that in our model, or if we do it outside the model to prepare our data. Either way is fine. It can also be done in Python. So in the conversion toolbox, there's polygon to raster, and you would put the soils in, and then the soil code here is the column or attribute that contains a code for each unique soil type. and then the name of the output layer, soil, and then how we want to do it, how we want to do the aggregation by maximum combined area, and then the cell size of the environment, which would be 1,000 meters by 1,000 meters. So the polygon to raster in this case will do the as we've seen before, it undertakes resampling in that process of converting to raster, and we want to choose maximum combined area for that conversion. So the outgoing cells are more representative of the majority of whatever type of soil was within that particular cell. And then we create a raster variable from the result, here, soil. And that will leave us with a new layer called soil and a raster variable called soil that contains 1,000 by 1,000 meter cells that will match up with the precipitation and temperature layers. Then for elevation, we have a two-step process, or two-step model, a model with two processes. The first one is converting from WGS84 to UTM51. That's called projection. So we use the project raster tool for that. We specify our output coordinate system, the resampling technique that we want, and the output cell size. So for elevation, because it's approximately 90 by 90 meters, the output cell size will be 90 meters. Because elevation is a continuous variable, we'll use bilinear interpolation in the resampling. And again, we're not changing the cell size drastically. We're keeping it or preserving the resolution as much as possible here. So we want to use bilinear. And we specify the output coordinate system, and that produces then a layer which is in WGS84 UTM51 North. And that layer then has to be aggregated. Now, the cells have to be aggregated to 1,000 by 1,000 meters. So we now have a bunch of 90 by 90 meter cells inside each 1 kilometer output cell that we want. So I'm not showing them all here, obviously, because it would be lots of them, almost 100. So how do we then want to look at the elevation values in here? So in these original 90 by 90 meter cells, they'll have a whole bunch of different values, etc. So how do we want to deal with that? Well, resampling doesn't make sense here at all. And that's one of the biggest mistakes people make when they're scaling up raster data that's continuous, is they use the resample function. It's completely inappropriate for this type of work. What's required here is that we say what statistical value or summary of the values within the new cell size should be taken from the constituent cells in the old raster. So for example, here, things that would make sense would be a mean. So the mean of all the, or the average of all of the 90 by 90 meter cell values should be assigned to the new 1 kilometer by 1 kilometer cell size. And there's an assumption in using the mean that within that 1 by 1 kilometer, the 90 by 90 meter values are normally distributed. You could take a median, for example, instead of a mean, if you're not sure about the normality of the cells inside of them. So to do that, we use block statistics. Block statistics assign to each cell within a defined block size, like 1,000 by 1,000 meters, the value, a statistical summary value of all of the cells that were considered within that block. So like the mean would be assigned to each of the original 90 meter cells within the 1,000 by 1,000 meter cell block. This is the process here in the model builder, which we'll do, of course, and Python has the same thing. We can have a data management tool, project raster, not the regular project. Project is used for vector. Project raster is used for raster projection. And that's where we turn elevation from into a DEM. We'll just call the output DEM. The spatial reference, we may exclude it because we'll set it in the environments, the global environments. And then the type, which is bilinear, and the output cell size. So as long as the output cell size is similar to the input cell size, we use bilinear during the projection. In other words, you don't project and change the cell size drastically at the same time because there's no appropriate method in the project raster tool to do so. So once we have that, we'll have a new layer called DEM. Then we make a neighborhood object, which you've seen before. In this case, instead of a circle, it'll be a rectangle of 1 kilometer by 1 kilometer in map units. Once we have the neighborhood, we have our DEM here. We can then use the block statistics to look within each 1,000 by 1,000 meter cell, or block, 1,000 by 1,000 meter block, and take the average of all the cells that it finds in there, the values of all the cells. So block statistics input is the DEM. That's the projected DEM. Neighborhood, right there. And we want a mean, the most common one. And once we have that, we have a DEM raster variable at 1,000 by 1,000 meters. And that DEM will already be at 1,000 by 1,000 meters because that'll be the environment cell size. So here, for example, you can see the difference between the original elevation right here on the left and the projected and generalized elevation on the right. And what you see is a lot of detail in here in the original because it's at 90 meters, and then it looks almost blurry in the projected one because you lose detail by taking the average, obviously, over a 1 square kilometer area. So now we go back and revisit our original table, and we fill in things according to the data we have now after that pre-processing step. So soils, we look at our soils layer, our new layer called soil, and we check its spatial reference, its format is a raster, and its resolution. And that's all done in the properties of the soil layer. We don't have to do anything to the next two because they were already checked to be this in the right format and size and everything in alignment. And then elevation, we have a new layer called DEM. We have to check that it's in WGS 8451 North. It's raster, and we check the cell size as 1,000 meters. And then what we can conclude then, if everything is the same in all of the columns for the spatial reference, format, and resolution, we know we can now start our modeling. And we build a model with these conditions where precipitation is between 1,600 and 4,000 millimeters per year, slopes between 1 and 5 degrees, soil type loam, and minimum coldest temperature greater than 12 degrees Celsius. And these are the conditions, and this is what the model will look like after that. And we'll do that in the example, the worked example in ArcGIS Pro. We'll also do the example here, which is the same thing, but in the Python window using a Python script. And it's a few lines. And we'll do it again step by step in the example. And durian, of course, is the king of fruits, but it's just as a bit of a background, it's a spiky fruit. It's very large. They can weigh many kilograms in size. It's considered the king of fruits. It's been called the king of fruits because it is probably the most pungent and tastiest fruit in the world. Much better than many of its cousins. It's related to, or it's in the same family as chocolate, for example. So the cocoa bean and whatnot. My favorite fruit by far is the durian. To start with, I'm going to go to folders, and I'm going to go back to where I have my data folder from the module 3.4. And in here I see a geodatabase called Philippines, and I'm going to expand that. Then I can see some of my layers are here, like total rainfall, temp, coldest. I can drag those in. So I'll bring in the total rainfall first, because this will become my control raster for everything else. So here we are in the Philippines. And I'm just switching to decimal degrees here to show approximately where the Philippines is. And if you look at the bottom of your screen in the status bar, you can see that the southern part of the Philippines is about 5 degrees north of the equator, and the northern part of the Philippines, in the large island anyway, is about 18 degrees above the equator. So it's well within the equatorial region. So I have now the total rainfall. I'm just going to symbolize that, and that's in millimeters, by the way. I'm going to symbolize that on the Appearance tab, Symbology, Stretch, and I'm going to give it something maybe brown to green or whatnot, if I can find something that's brown to green. So here I have a brown low rainfall to green heavy rainfall, something that is representative of dry versus wet. Now, the next thing I'm going to do is go to my Analysis tab, Environments, and set my environment variables to this layer. So the output coordinate system is still the old state plane Vermont one. So I need to change that to total rainfall. The extent as well must be now total rainfall, because we're in a completely different place in a completely different coordinate system. Cell size, total rainfall. Mask, total rainfall. And snap raster, total rainfall. So that's fundamental that we set those. I'm also going to have a look at my layer properties, and I'm going to choose the source item and have a look at the raster information to make sure I have everything that I remember correct. Here we have cell size X and Y, 1000 by 1000. And I can go down and check my linear units under the spatial reference. And those are meters. So we have a cell size of 1 kilometer by 1 kilometer. And we are now having the WGS 84 UTM Zone 51 North coordinate system. Next, I'll go back to my catalog, Philippines, and I'll bring in the temp coldest. So this is the minimum temperature of the coldest month, and that ranges from 6.3 to 23.8. Obviously, in the highlands will be 6.3. And I'm going to re-symbolize that. Appearance tab, Symbology, Stretch. And I'll change that, since it's temperature, something from red-blue. There's a red-blue. And here I have the blue should be the coolest temperature, so I want to reverse that. So I'll click there and say Formats Color Scheme, and click on the Reverse Color Scheme. There we go. There. So now we have the warmest areas in reddish, red, and blue for the darkest, and it goes from blue, green to red in between. And that again is just for symbolization purposes. This has no effect on analysis in any way. Let's go back to catalog now. So let's have a look at elevation. If I bring elevation in, it will project it on the fly to this current coordinate system. So if I look at the elevation properties, source, spatial reference, it's just WGS 84, longitude, latitude. In raster information, it has 0.00083 degrees, X and Y. And that's approximately, well, that's 3 arc seconds. And that is, in real world units, is approximately 90 by 90 meters at the equator. If I zoom in on this raster, really close, just on that elevation one, you can see that they're not perfectly north, south, east, west. So there's clearly, if you look at the top here, you can see that we don't have cardinality to these raster cells, and this is a raster that has been projected on the fly. This is one of the ones that we have to project to our coordinate system so that we have a cardinal orthogonal raster with approximately a 90-meter resolution. And then we use block statistics to bring it up to a 1 kilometer by 1 kilometer raster. And then I'll bring in soils. And I'll click on symbology, unique values, and look at, we have here soil type, soil code. For example, soil type, we have loam and non-loam, and that's kind of what we're looking for. There's also soil code, 100 and 200. So if we look at the attribute table for soils, I'll just float it up here for a second. The soils attribute table has a soil description, a soil type, loam, non-loam, and then a soil code. Loam is 100 and non-loam is 200. So when we do a conversion of soils to raster, when we encode it, we want to use the soil code to become the new cell values for the raster. And we have to remember that 100 means loam and 200 means non-loam in the output raster. And I'll zoom back out to the temp rainfall, zoom to layer. So next, I'm going to go over to catalog. And in the Philippines geodatabase, I'll make myself a new toolbox. New toolbox, so right click, new toolbox. And I'll call it Durian. And then in Durian, I'm going to make myself a new model. And that opens up the model window here. So the first thing we have to be able to do is our pre-processing. Soils is a layer, which is a vector layer, and we need to encode it to raster. So soils will be the first thing I'll bring in here. There's soils. Zoom in a bit for now. So there's our soils input. And then we're going to go over to the geoprocessing tab, and then into conversion tools. And in conversion tools, we have to raster, and we want polygon to raster. So we'll drag that up here. Soils will be the input vector layer. So I'm going to connect that to polygon to raster as the input features. Then I'm going to double click on polygon to raster because we have to change the parameters to match the best possible encoding methods for a vector layer, which is categorical. So for example, here it says soils, and then the value field is what will be assigned to the cells. We don't want that to be object ID. We want it to be the soil code that I just talked about, where 100 is loam and 200 is non-loam. We leave the output raster data set. We don't touch the name of that because it's intermediate. And then the cell assignment type, we want maximum combined area. For a given 1 kilometer by 1 kilometer cell, if it's more loam in there, then the cell will become loam. If it's more non-loam, the cell will become non-loam. We don't have a priority field, and the cell size has already been filled in here because from our environment parameters, our application level ones up here in the analysis tab environments. Total rainfall, and I click OK. So the output then is soils raster. So I'm going to rename that to soil raster, like that. So that's our first part. And just to see that it works, it'll become part of our larger model. So now I'm just going to click on the polygon to raster and right click and say run. So run runs just that particular tool. And then we see the drop shadow, meaning it's in an already run state. And it added it here to the table of contents, the contents pane. So I'm going to go back to my map and have a look at that soil. And there we go. It looks good. 100 loam, 200 non-loam. And I'm going to double check the size and properties to make sure it's a raster information. It shows 1000 meter by 1000 meter, which it does here, the cell size. So that's very good. And the spatial reference will be still the same as it was before, the WGS 84, UTM 51 North, right here. And everything is good. So that part of my model works. So I'm just going to revalidate it, and I'll remove the soil raster from my table of contents. And generally I want to remove things I'm not using anymore. So again, soil raster is just an intermediate for the model, but I was just making sure that it worked properly. Here you'll see me delete the soils layer, but I actually do need it to complete the model. So I'll bring it back in later on. Now the next thing we need to do is get the elevation layer projected into UTM zone 51 North, and then change the cell size, upscale it. So elevation will be the next one I'll bring in. I'm just going to move this one over up here, and I'll bring in elevation right there. And I'll save my model as well at this point. I'll be saving often because it's a large model. So here we have elevation. So elevation, we need to project using the Project Raster tool in the Geoprocessing tab in the toolboxes. So that's under Data Management Tools right here. So Data Management Tools. And then we go down to Projections and Transformations. And then we want to go into Raster, Project Raster, and we bring that in. And my input raster will be elevation. So I'm just going to connect that right away to Project Raster as the input raster. Then I'll double click on Project Raster. So the output coordinate system is taken from the application level environment settings. So it's the same as total rainfall, WGS 84 UTM zone 51 North. The resampling technique, because this is continuous data, we want it to be bilinear interpolation. And the cell size here, it suggests 92 by 92. So instead, we're going to say 90 by 90, right there like that. It chose 92 by 92 because in the environments settings, in the analysis tab, we look at those, we have cell size projection method as preserve resolution. So it tries to preserve the resolution based on some basic numerical algorithms that it uses. But we want 90 by 90. It could even be 89 by 89 or 90 by 89. So in this case, 89x by 90y, but we'll keep them perfectly square. It's close enough to the 3 arc seconds. And so I'll click OK. Everything's been filled in there. So the output now, here I'm going to rename it as elev UTM 90. Just to remind me that's elevation in UTM with a 90 meter cell size. And I'm just going to check that works all right. So I'll right click on Project Raster and I'll click Run. And this can take a few seconds because it's a computationally intensive process to reproject the raster. Remember, it has to make a whole new raster in the new area and then figure out, based on the locations of the old cells, the 4 closest ones to each new cell, and then linearly interpolate a value. So that's done. And we see the drop shadows. And I'll just right click on elev UTM 90 and add to display so I can check it out. So the first thing you'll notice is that we no longer have the same minimum and maximum. In the original elevation data, the minimum was -197. Now it's -195. The maximum was 2933 meters, and now it's 2929. So just projecting the raster and maintaining the resolution leads to modifications in all of the cell values. So let's have a look at it here, and I'm just going to zoom in again to this layer really close so you can see the cells. Try to find an area where there's contrast. So you can now see, or you should be able to see, that the cells are now cardinally oriented. And if I turn off elevation UTM 90 and turn on the original elevation, see, they're a bit tilted. So there's some rotation there because of the georeferencing of elevation into the coordinate system called on-the-fly transformation. So now it's cardinally oriented. Everything is good the way rasters have to be for analysis. And the original one is skewed a bit and rotated because it's just been approximated into this space. So I no longer need elevation. I'm going to remove it. And we also know that when we do a project raster, all the cell values change. So the next thing we need to do, I'm going to go back to model builder here. I'll just validate. I need elevation in there actually. So I shouldn't have removed elevation and soil. So I'll bring them back in because I need them for the full model when we run it. So I'm going to go back in, bring in the soils and elevation, the original one. We need them in there, and I meant to remove the ELEV UTM 90. So the elevation project raster, I'm just going to rename that again. So I'll rename that ELEV 90 UTM 90. So the next process on the elevation is going to be to use block statistics to upscale it. So I'm going to click on my geoprocessing tab, go to the geoprocessing pane, and I'm interested now in spatial analyst tools. So I go down to spatial analyst tools and then neighborhood, block statistics. And I want to bring that in there like so. I'll just bring it over here so you can see it. And I'm going to connect my ELEV UTM 90 to block statistics because this is the upscaling part where we go from 90 meters to 1 kilometer by 1 kilometer cells. So I have the input raster, it's ready to run, but I have to customize it in block statistics to say, that I'm giving it the parameters I want. So the neighborhood will be a rectangle and the width will be 1,000 by 1,000 meters. Because that's our new cell size. And units are map units in this case. And then we have the choice of these statistics. So we have the median, the mean. We could also choose maximum, range, standard deviation, sum, are all possible things. But we want something that's going to be representative of the most likely type of value you're going to find within a 1 kilometer by 1 kilometer block. And that's going to be the mean in this case. And make sure that ignore no data in calculations has a check mark in it. So that's good there. Now my output will be, I'm going to right click on that and rename that just ELEV. And that's going to be the elevation that will go into analysis, getting slope from it. So we have our soils converted to a raster up here of 1,000 by 1,000 meters, and then ELEV. And again, I'm just going to test this one, and I can test as I go. And I'll just say run. And it's done. And so I'm interested in here, ELEV, so I'm going to right click and say, well, click off of those. Click on ELEV, right click and say add to display. For elevation, after block statistics, we have a range of -71 below sea level to 2,851 above sea level. And there's one block, for example. You can see one cell size here and all the cells that would be in there underneath it. So this value here is 123. And that's the average of all the values you see here, all the cells that were within that 1 by 1 kilometer cell. And so on ELEV, I'm just going to double click and check that everything is correct, that the raster information. And we have a cell size of 1 by 1 kilometer. And a spatial reference should be UTM 51 North. Yes, that's good. So I no longer need right now ELEV in there or ELEV UTM 90. So I just remove them from my contents over here. Then I'll just validate my model so far. And I'll also do a auto layout, just like that. And I'll move it over this way, since I have more things to add now. So we now have our soils raster. We already have, we need our temp coldest, so we're going to bring that in here. That's another input. And total rainfall is another input. So we can work on one at a time. So for soils, we need to select loam. And that's pretty easy. That's just an equals to. And we know the code for loam is 100. So anything coming out of the soils raster that has a value of 100 will be loam. Everything else will be non-loam or 0. So 1 for loam, 0 for everything else. So I go back to my spatial analyst tools, math. And then in math, I go to logical and equal to, and I drag that into soils. Now I connect soils to equal to as the first raster, double click on equal to, and put the comparison value here, 100 for loam. We click OK. And then we rename that constant to 100 so we can follow our model later, read it. And the output will be called loam. There we go. I'm also going to click on save and move these things up over here again. There we go. So loam is one of the final layers that we need in our model. Loam, non-loam, and that's what this will provide. Elevation, we need to get slopes. And the slopes, if you recall, have to be between 1 and 5 degrees. So I'm going to need a greater than and a less than. So I'll bring in one greater than, and I'll bring in one less than. Or let's do equals. So greater than equals and less than equals to get that 1 to 5 complete endpoints. So a less than equal and a greater than equal. And I'll connect ELEV as the first input to both of those. So this is a parallel process now running on ELEV, a not equal and a greater than equal. Oh, not, that's the wrong one. Not equal is not what I meant to bring in. That should have been less than equal. Just delete that and bring in less than equal. I guess I accidentally clicked on the bottom one. Less than equal, here we go. And connect ELEV to that. Then for less than equal, has to be less than an elevation? No, I forgot slope. I can't do any of these without slope, so I'm going to click on each of the arrows that I added to connect ELEV to greater than equal and less than equal. And now they're no longer connected. I'll just move them out of the way over here a bit. I need slope first. So I go down to surface and then go back down again to slope and drag that into for elevation. So I'll now connect elevation to slope as the input raster. And the output will be slope out. So I'll rename the output slope out. Like so. So I did that to show you that once you've connected something, you can just click on the arrow to delete it. And once you deleted the connection from a input to a function or process, then it's no longer connected. It won't affect anything. Because here now it's actually slope out that I want to connect to each of these. So input raster 1, and here for greater than equals is input value 1. Now it might be good here to do a auto layout. And it lays out things like that in this case. So now I have my slope. So elevation moved down here. We project it into a 90-meter resolution in UTM zone 51 north. And then we use the block statistics of 1 by 1 kilometer blocks to get the mean of all the elevation cells within each block. And that creates elevation here at a 1,000 by 1,000 meter scale. And then we get the slope of that right here. And the slope then is something we're interested in determining between 1 and 5 degrees. So less than 5 degrees. So I double click on less than and the comparison will be 5. Because we want less than 5, so I'll put that there and I'll right click and say rename, and I'll put 5. And greater than 1, greater than or equal to 1. So double click on that and put a 1 for the second input raster or constant value. Just a 1. Like so. And then I'll rename that as 1. Then the less than 5, I'll rename over here. I'll call that one the output of less than equal to 5. I'll call it LTE5 for less than equal to 5. And this one greater than equal to, so I'll call it GTE1. Like so. Now I have two separate rasters, one that shows all slopes less than 5 and another separate one that shows all slopes greater than 1. The intersection of these two then gives me where the slope condition is met for Durian cropping. To put them together, to intersect them, I could multiply the two together, but since I'm using Boolean layers, this is a Boolean layer now, both of these, I'll use the Boolean and. So I'll go back under Math, Logical, Boolean and I'll bring that in and just scroll over a bit here. And I'll connect LTE5 as the first and GTE1 as the second. The order doesn't matter. So now I have a Boolean and the output raster is going to be the slope condition. So I'll rename that. Slope, COND, I'll put all the capitals. So that's the slope condition. So now we finished the loam and the slope. And I'll just do again an auto layout and fit to window here, like so. The elevation, we now have from elevation a slope condition. From soils, we have our loam condition. Now we need temp coldest. And that has to be greater than 12 degrees. So that's pretty straightforward. All we have to do is bring in a greater than, right there, greater than. And it's strictly greater than here. So I'll bring in that strict greater than, and I'll connect temp coldest as the first input. And then the second input will be 12 degrees. So I'll put 12 there, and I'll rename that 12. Like so. And a quick auto layout again. The output will be suitable temperature, so I'll call it temp cond for temperature condition. So TEMP COND, like so. So we now have our temperature condition, loam, and slope. Now total rainfall has to be between 1,600 millimeters per year and 4,000 millimeters per year. So that means I'm going to need to do the same thing that I did with slope. I need a greater than, equal to, and a less than equal to. So I'm just going to move that over here a bit so I have some space. And we'll auto layout it afterwards. So I need a greater than equal and a less than equal. And also, I'll know, because the outputs of these are both Boolean, I need a Boolean and to put them together to get the regions which are between 1,600 and 4,000 millimeters per year of precipitation. So I'll start with my greater than as input raster 1 and total rainfall to less than as input constant value raster 1. Then for the greater than, I just double click on it and it's going to be 1,600. And I click OK. And I rename that 1,600. So I rename to 1,600. Then for the less than, I double click on it. And we want less than or equal to 4,000. So I put 4,000 in there. Click OK, and then rename that as 4,000. Now, for naming the outputs, the first one will be, I'll call it GTE 1,600 for greater than equal to 1,600, rather than greater to 1, the default. So GTE 1,600. And this one will be LTE 4,000 for less than or equal to 4,000 millimeters of precipitation. And then both of these go into the Boolean AND as input 1 and here input 2, like so. And I have to scroll over a bit more. And the output here then is going to be the rainfall condition. So I'll call it rain, C-O-N-D. So I'll right click and say rename rain, C-O-N-D, because this is now the conditions for rainfall. Like so. Then I'll do an auto layout again. And you can see, oh, there we go, to fit it all in. There we go. We can see them now. So now we have all our conditions. We have temperature, loam, rainfall, and slope conditions. Now we just have to put them all together. And we'll do that with Boolean ANDs. And we can only do 2 at a time. So we'll need, if we have 4, 1, 2, 3, 4 conditions, we'll need 2 Boolean ANDs for each 2 of those. And then a third Boolean AND to put those second intermediate Boolean ANDs together. So temp condition to the Boolean AND up here, input 1, loam to that, input 2, rain condition to that Boolean AND as input 1, and slope condition as input 2. And then here, input 1 to that Boolean AND, and this last one to 2. Now for naming these intermediate ones, the first Boolean AND is temp cond plus loam, so I'll just call it that. So I'll say rename. I'll just call it temp loam, C-O-N-D for condition. This one is rain and slope. So I'll rename that here to rain slope cond. Like so. And then over here is our final output, which is Durian suitability. So I'll call that suitability. Oh, I don't want to label out there. Rename suitability. So get rid of that label, and I'll right click on suitability and say add to display. That's the only one we actually need to or really want to see from our model. So now I'll click on the auto layout. There we go. And I'll have to zoom out quite a bit. And that's how this model looks with the auto layout. So you can see it's visually very complex. But if you read it from an input to the end, you can follow the logic. So elevation is projected, and then block statistics are applied to get slope. Slope then is assessed to be greater than 1, and then again less than 5. And then greater than 1, less than 5 are put together in a Boolean AND to give us the slope condition. Then if we start over here, that's the input. If I just move that out a bit, you can see it better. That's the input for this branch. So total rainfall is the input, and we're interested in rainfall between 16 and 4,000 millimeters, 1600, I should say, and what is that? 16,000? No, 1,600. Yes, of course, 1,600 millimeters and 4,000 millimeters. So we have a greater than and a less than operating on that. One to get greater than 1,600, the other one less than 4,000. And then those two are put together in a Boolean AND to get the rain conditioned. And then rain conditioned and slope condition are put together in a Boolean AND to get the intersection of rain condition and slope condition. And then if we look up over here, I'll just move that out a bit so we can see the inputs over here better, like so. We have soils and rainfall. Soils has to be encoded to raster first to get soils raster. And then we are interested in where soils raster is equal to 100 to create loam. Temperature of the coldest month must be over 12. So here we have a greater than 12, and that gives us a temperature condition. The temperature condition and loam condition are put together with a Boolean AND to get the intersection temperature and loam. And then temperature and loam is intersected with rain slope condition to get our suitability at the end here. So now I'll validate the model. And everything is good with the validation. I'll save it, and then I'll run. I think I might have left on 1 or 2 add to displays in there, so we might see more than just the final one added to the display, but that's okay. We'll just remove them. We don't need them. So we can watch the progress of our model here. So right now it's doing that projection. And you can see by the speed that the bottom branch here, working with elevation, is the most computationally intensive because of the projection and block statistics. After that, it's quicker. And then we have drop shadows. And everything is successfully completed. No errors. And it's done. And so suitability now is right there. It also added a couple other ones that I forgot to turn off the things for add to display, but it's no matter. We're interested now in suitability, so we go back to our map. And again, I'll make 0 black, and the other is green. So all the green areas here meet the conditions for Durian growth. So now the government could look at those particular land parcels, or whatever they might be, and decide what other things might be important for a political or environmental viewpoint in choosing which of those to choose for Durian plantations. We can accomplish the same process as we did in the cartographic model to produce the suitable regions for growing durian. Here I'm starting in a fresh new project, and that's because I was having issues in the previous project because I had so many different maps and stuff in that project going and data in the tools, and it was causing some issues with some processes. So when I'm having continuous issues with something in ArcGIS Pro, I'll often try making a fresh new project and then bringing the data in and trying my process just in that brand new project to ensure that things are working as I would expect them to. That being said, I'm going to go to my catalog and I'll have to reconnect to my folder, my data folder, which is on my C drive. That's where I put it, the data folder from the module 3.4. And then in data, Philippines, and I'm going to bring in, first I'll just bring in soils. Then I'll bring in elevation, temp coldest, and total rainfall. So I'm going to go and open up in my analysis tab, environments. And I'll set my critical environments to match the total rainfall. So output coordinate system, total rainfall. Extent, total rainfall. Cell size, total rainfall. Mask, total rainfall. And snap raster, total rainfall. I will also change the cell size projection method to preserve resolution. And I'll click OK. So those are my global or application level environment settings. And now I'm going to open my Python window. So I have a brand new Python window here, first session of the day. And I'm just going to resize it a bit, if I can catch the edge. Well, it's all right, we don't need to see that. We might need to see some tools though. Okay, so I start with my imports from arcpy.sa, import all. From arcpy.management, this is new, import all. And that's because we need, under data management projections and transformations, the project raster tool. And then from arcpy.conversion, import all, because the conversion toolbox contains our encoding method, polygon to raster, like so. I'll also import my env from arcpy import env. And I'll just check to see that my global environments have been passed down to the Python window. So I'll just say env dot output coordinate system, for example. As we can see, we have the spatial reference object coming out as from env.output coordinate system, and that should be the same one if we look at the name of that dot name as we specified in our global environments, which is WGS84 UTM zone 51 north. So we're good to go to start our processes. We'll start with elevation because it requires the most processes to be operated on. So elevation is already in meters for this data. So unlike many US data, much of the rest of the world uses the metric system. So we have meters of elevation vertically, ranging right now from 197 negative to 2,933 meters in the highlands. So the first process we're going to do to elevation is going to be to reproject it into a 90 by 90 meter cell size into UTM zone 51 north. For example, I'll make a raster variable out of elevation. I'll just call it E for now. ELV equals raster, and then I'll choose elevation here. Once I have the elevation now variable as a raster, the next thing I'm going to do is project it. So I'm going to call the output ELV90 equals project raster. The input to be projected will be ELV. We'll just wait for that to come up. And for the rest of the syntax, I don't remember it off by heart, obviously, all the syntax. See if it comes up. No, sometimes it just doesn't show up. So I'm going to go back to my geoprocessing toolbox. I'll go to Toolboxes, Data Management Tools, like so, and then down to Projections and Transformations, Raster. And here we have the project tool, Project Raster. So I'll click on that and I'll click on to open the help file, which will tell me the syntax. So in the help file for Project Raster and any tool in our toolbox, you can scroll down and it will give you the syntax right here. The syntax specifies the order of arguments and the names of the parameters, such as in raster, out raster core system, resampling type, cell size, etc. Now, for each of these, we can see that below the syntax, it tells us what that parameter is. It's a raster data set that will be transformed to a new projection. And what the data types must be to satisfy that parameter as arguments. Mosaic layer, raster layer, and we're working with raster layer. And then we need an out raster. So that's going to be any of these things as a name. It could be a full path, a name, or just a name if you wanted to go into the default geodatabase. It's a geodatabase raster, which we'll be using. And then the output coordinate system. The output coordinate system of the new raster data set, and it has to be a coordinate system. And that is a spatial reference object right here, spatial reference object. We can get that right from our environments by saying env.output coordinate system. That returns a spatial reference, the spatial reference that was set in the application level environments, which again here is UTM zone 51 north, WGS 84. Then the resampling type, and we're going to use bilinear because we're going from one cell size to approximately the same cell size in real world units. And our data is continuous data. So elevation is considered a continuous variable. So we want to use that bilinear interpolation, so we don't end up with artifacts like stair steps and stuff within our raster outputs. And then the cell size that we want. In our case, we want a 90 by 90 meter cell size as the output. And so we'll just put 90 for that. The rest of them don't apply in this case. We'll put things in this order. So ELV is the input, and I'll call the output LEV 90. And then my next one after that, let's go back to the project raster, is the output coordinate system. So that's going to be env.output coordinate system. We can just put that right in there because as you saw above, when we said env.output coordinate system, it provided a spatial reference object, which is what is required for this particular argument. Then the resampling type, and I want bilinear. And finally, 90 for the cell size. And this will be one of the slower processes because it's computationally intensive. And what's happening here again is that we have the original elevation warped or georeferenced into this space that we're working with. And because the elevation actually has a coordinate system, equations are used. So it's a definite transformation, an exact transformation to put in from WGS 84 to UTM zone 51 north. And a whole grid is created, and then we used bilinear resampling to find the values for the new raster layer. And you'll also notice here that the original elevation went from -197, now it's -195. And it was 2933, now it's 2929 is the maximum. So just the act of projecting our raster layer from one coordinate system to another with approximately the same cell size changes the values of elevation somewhat. So that's something you have to keep in mind. That's a source of uncertainty. So I don't need my original elevation in here anymore, so I'm just going to remove it. So now I have LEV90, and I'll make a raster variable out of that. I'll just call the raster variable LEV90, and it'll be equal to raster ELV90. So here in our previous statement, ELV90 returns a results object. A results object in ArcPy Python just contains information about where the actual raster is, as well as other information about the raster, like its cell size, its coordinate system, and all that type of stuff. But it's not a raster variable by itself. The raster is LV90 here. And if we say raster function, and we put in there the results object, ELV90, then LV90 will become a raster variable. So we'll put that like so. So now LV90 is a raster variable. We could have also said LV90 equals raster, and then in quotes LV90, because it's in our table of contents. So we now have a raster variable again for the ELV90 being referenced. So the next step is block statistics. For block statistics, we need to specify first the block size. So I'll call my block size NBR hood for neighborhood, and that's going to equal to NBR rectangle 1000 by 1000, and we want map units. So that's a 1 kilometer by 1 kilometer block size. Then we can use block statistics. So I'll call the output here, DEM, I'll call it DEM equals block statistics. And then input will be LV90, the neighborhood, NBR, that we just created, neighborhood, NBR hood. The statistics type, to summarize all the 90-meter cells within that 1 kilometer block. And we want to take the mean. And that's all we need to specify for that. And then we hit enter. DEM will now contain 1 kilometer by 1 kilometer cells. And let's just validate what we just did by looking at the data here. So from elevation, we went to LV90. So that, I'm just going to double click on that, click on the source, and then the raster information to see what size the cells are. They're 90 by 90 as we requested. And that also should be in the UTM-51 North spatial reference, and it is, so that's good. So now let's check the block statistics. So the block statistics, this layer, DEM, should have a resolution of 1 by 1 kilometer now, because the output resolution is specified in environments here. Remember, the same as total rainfall, which is 1000 by 1000 meters, or 1 kilometer or square kilometer cells. If we hadn't specified that in environments, then our output cell size would have been the same as the input. In other words, 90 by 90 meters. So the way block statistics worked in this case is that it assigned to each cell within a block the average value of all cells within that block, and then used nearest neighbor resampling to determine the 1 kilometer block cell size for the 1 kilometer output cells that we wanted. That part was done in the background, and in this case it's okay here because all the cells had the same value within the block. So the nearest neighboring will have just one of those cell values, which is the same as all the other ones. So we'll double click on DEM and then source raster information. Cell size has to be 1000 by 1000, which it is now. And the spatial reference is UTM-51 North, so that's great. So that's all ready to be used. So now that DEM is complete, we can figure out our slopes. So we want slopes greater than 1 and less than 5 degrees. First, I'll make a slope variable. I'll call it slope equals slope DEM. And you can see it adds it to the table of contents. Then I'll create a single expression to get the data between 1 degree and 5 degrees, inclusively of 1 and 5. I'm going to call this slope cond. For the slope condition, that's going to be equal to parentheses and parentheses. And that will be slope greater than or equal to 1 and slope less than or equal to 5. And notice here, I have to do this because of order of operations. Because and, if you recall, the order of operations for conditional operators, or all operators, and has precedence over greater than equal to or less than equal to. So if I didn't do this, it would try to compare 1 and slope. And it makes no sense to say 1 and slope, because 1 is a single value and slope is a raster. So I'd have a ambiguous statement error. So I have to be careful here to use parentheses to ensure that the conditional, or the relational, I should say, the relational parts of this statement, slope greater than or equal to 1, happens to create a output raster that's 1 and 0, and that slope less than or equal to 5 happens for a second, so that I have, again, another layer with 1s and 0s, where 1s mean the slope is less than 5, and 0s mean it is not, before they're put together, intersected, to get where both conditions are true at the same time with an and, to create slope condition. And if we want, we can have a quick look at it. I'll just turn off soils here. So there's the slope condition variable, 0 and 1. And I'll just make that black and green. Good high contrast. So everywhere that's green right now has a slope between 1 and 5 degrees. So we're now done with the slope condition. The next one that requires processing is the soils layer. So remember soils, if I just open up the attribute table again, it has a soil code here. And the soil code tells us 100 for loam and a value of 200 for non-loam. We're going to use the polygon to raster tool and the maximum combined area resampling to convert soils from vector to raster using that soil code field. So I'll call the output here soil equals polygon to raster, and the input will be soils. And then which attribute do we want? Soil code. That's what we want converted to raster. So the cells take on values of 100 or 200. So polygon to raster, soils, soil code, and then it's not giving me the further information here, so I have to go to the help file for polygon to raster. So that's in conversion tools, to raster, polygon to raster. So I'll just open that up and click on the help file. Polygon to raster conversion. And I'm going to scroll down to see the syntax. So in features, and then the field we've specified. Now the output raster dataset we have to specify. So the output raster dataset we'll call, again, that has to be in quotations. It can be a full path or just the name. So it goes into the geodatabase, the project geodatabase. And I'll call this output I'll call it soil. Soils as well. Then maximum combined area. So the cell assignment is there, and we don't have a priority field, and the cell size will be taken care of by the global environment settings. So I hit enter. And again here, soil will be a results object, not a raster. So to make the soil raster, I'll just call it soil again equals raster soil, like so. So now soil is referring to the raster called soils. So it's a raster variable now. Then from soil, I want wherever it equals 100 to be 1 and everything else 0. So I'll make soil conditions. Soil cond equals soil equals 200. So that equals means, of course, the logical equals. And I can have a look at that over here. So there's the soil condition. And I'll make 0 black and 1 green. So black is non-loam and green is loamy soils. So we now have the soil condition and the slope condition finished. So now we need to do the rainfall and temperature of the coldest month. So the rainfall is the next one that requires attention. First we'll make a raster variable out of precip. So I'll call it precip equals raster, and then that's total rainfall. Now I'll make my precip condition. Precip cond equals parentheses and parentheses. Because remember, it's a specified range of precipitation between 1,600 millimeters and 4,000 that we're interested in. So we need to use relational and conditional operations here. Inside the first parentheses, I'll say precip greater than or equal to 1,600 and precip less than or equal to 4,000. So we just look at it over here, and I want black and green. I was way scrolled down somewhere. So everywhere here that is green is suitable, and the black is not suitable in terms of precipitation. So finally, the easiest one here to do is the temperature of the coldest month. All we care about is that greater than 12. So I'll call this temp cond, and that'll be equal to raster temp coldest, and it must be greater than 12. So notice here I didn't bother creating a raster variable of temp coldest, so that would have required an extra statement. So here I just do it in one statement because that's all I need for the condition, is to find areas that have greater than 12 degrees. And that'll be way at the top here. There's a temp condition. So everywhere here with that's green is meeting that condition. I'll make the 0 black again, make it easier to see. So in the very highland areas, they can get lower than 12 degrees, and some of these little islands up here as well. But generally everywhere else is above 12, which is good. So we now have all our conditions to create our suitable map. So I'll call this Durian as the output, equals temp cond and soil cond and slope cond and so precip cond. And I did this all in one statement. And that will create a suitability map for Durian. I just noticed as I'm looking at this right now that I made a mistake up here. Soil cond equals soil equals 200. Recall that 200 is non-loam, 100 is loam. And so I need to redo that. So I'm just going to hit my up arrow like so, change that to 100, and it will overwrite it. Then I just have to run the last one again. So one of my things was wrong, the soil condition. So I just hit my up arrow and changed 200 to 100. Now I just have to rerun the last line. The other ones are still fine because they're not affected by the soil condition, I should say. So I just have to repair a soil condition, very easy that way, and then rerun my last line to get the correct output. So I'll just close that. And again, I'll make the black and green. So that's the final map, and that's the same as, I'm just going to turn that off, the soil condition. That's the same as the output of the cartographic model. So that's the way we do it in Python. And you see it's quite easy to fix a small mistake like that. You just have to hit your up arrow, find the offending line, change it, and decide at that point, do the other lines, any of the other lines here, do they depend on soil condition? No, only this one did. So then I just have to run that one. So you change the line that's offending, find out by examining your code if it occurred anywhere else, and wherever else it occurred, you would have to rerun those particular lines. And that's it for the Python example.